evening, everyone. So today we'll be doing triple integrals and spherical coordinates. This coordinate system is great when you're dealing with surfaces with spheres or cones. Okay, so if you really had a surface that was a cylinder, it's better to do things back in cylindrical coordinates. As we saw in some of the problems we did previously, you dealt with this, something combined with the cylinder. But we're doing triple integrals and spherical coordinates. This can be beneficial, make the problem easier to work if it's dealing with a surface that's a sphere, or maybe a cone, or both a cone and a sphere. So two things we're going to have to do is develop the volume element for doing things in spherical coordinates. I mean, remember with polar coordinates, what was automatic? That R? We're going to have to go get that thing going, right? Make sure we get that. So we're going to have to do that with spherical coordinates. So can you help me draw a nice picture here? I'm going to add some symbols to go spherical coordinates. This is what we had in cylindrical coordinates. You had a theta, and it looks distorted because it's three-dimensional, but there's a 90-degree angle right there, and then there's another 90-degree angle here, okay? But can't we call this distance x from here to here? Mm-hmm. So I'll do that. And the distance from here to here, y? All right, I'll do that. And then we call this distance right in there, from there out to here, r. Go the other way. So I just want to make sure everyone gets that triangle down. That's x, that's y, that's r. See the right triangle, Pythagorean theorem. And that's really polar coordinates, right? With the x and the y and the r. Then in cylindrical coordinates, we said, oh, you can have a variable z. And you can go up or down a distance z, and that allowed us to do cylindrical coordinates. Now we're going to talk about spherical coordinates. All right. So spherical coordinates, we're going to talk about how you take a point just right from that origin and then go straight out. So would you draw a line right here? And we're going to label this. We're going to call this distance rho. I know it's the same Greek letter they used when we did what? Density? But it's totally different from that density. It's just a variable we're going to use. It represents the distance from the origin, straight out in space, in three-dimensional space. That's the Greek letter rho. So you all notice we have another right triangle in here? Mm-hmm. And the right triangle has a length of r, it's got a length of z, those are the legs, but the hypotenuse is this Greek letter rho. So that's one of the variables in spherical coordinates. It's just the distance from the origin out in space. Kind of neat. There's another angle that we got going on, different from theta. So we're going to use another Greek letter, we're going to use phi. I need you to know where phi is. Phi is the angle formed from the positive z-axis outward. So right in here, I'm going to put a phi. Phi looks like that. Here's phi. Yeah. So here's phi. Phi comes out from the positive x-axis. I'll just draw an arrow like that. Phi is formed such that, it's adjacent to the positive z-axis and just comes outward. Which, if you can tell, that's why it makes it really kind of easy with cones. Because you just bend out like this from the positive z-axis all the way around, giving that cone formation. And I want you to draw phi somewhere else. Do you remember in geometry class when they said alternate interior angles are congruent? Do you remember that? So if that's phi, guess what I can call that angle? Phi. I can also call that phi. Do you notice this is parallel to the z-axis? So in your drawing there, would you also note that this can be called phi? It would be equivalent to phi. Right there, we can call that phi as well. Someone got it? This is going to be spherical coordinates. What are the three variables? Rho, theta, phi, and you got phi. Those are the three variables. What were they in cylindrical? In cylindrical, it was r, theta, and just a z, right? Or you're using the same data as before, but you also have a rho and you got a phi. Some textbooks do this in different order. They put the phi before the theta. I'm going to stay consistent with your textbook, and I noticed in your textbook, everyone, I'm looking at page 1033. This is the order they use. All right, but I do want to point, you look at another text, they might put that, when they plot these, the phi before the theta, because they're just different angles. Where is phi being formed? From the positive z-axis. So on that note, everyone, I'll use markers to help you see this. phi will never go higher than pi. Think about it. Let me just get out of here. There's the positive z-axis, right? That red marker. Well, if I form an angle from here, okay, if I get down to the xy plane, I only went 90 degrees, right? But the furthest I can go for anything like forming a sphere or a cone is straight down. And you notice that's the angle pi. So the limits for phi is 0 to pi. Phi only goes from that phi angle. Or excuse me. Phi will only go from pi to 0, never higher. That's its extreme. Because you just pull it all the way down. You might say, well, what about going back up? Well, we're talking about from the z-axis in all directions. So you got theta, here's theta, right? Theta's down there in the xy plane. You got phi coming from here. And then you have this distance rho we're talking about. Cool. So I don't know. Let's see, where would this point be? How about 3? Let's say theta is pi over 2. And let's say rho is pi over 2. Can you help me figure out where that point would be? If that's rho, that's theta, and that's phi. Can we just get a sense of where that point would be? Well, it's got to be how far from the origin?
3.
3. Distance of 3 from the origin. Theta rotated it, what, pi over 2. So where's theta is down in the xy plane. So it rotated 90 degrees from here, putting it on which axis?
Y.
The y-axis. And then how far did it come down? It bent down 90 degrees, which would put it right in the xy plane. So it would look something like this. Let's label this. There's your y-axis. There's your x-axis. There's your z-axis. This point would be right here. Do you notice that? Because it went a distance of 3, it rotated what? 90 degrees down from the positive z-axis, but it rotated pi over 2 this way. Cool. I just want to give you a simple point, because if I give you another bizarre point like pi over 4 or pi over 6, it might look out here or something, right? Where's this point? 3, 0, pi over 2. Where would that be?
That
So
should be
3 from the
x-axis.
origin, rotated 0 degrees for theta, sitting right on the
X-axis.
x-axis, but it came down.
5 or 2.
Yep, so this would be over here. Just to give you some easy points of where you can recognize where they would be located. Cool. Nice. Okay.
So
Well-
theta will always be between x and y, right? The angle.
That's right.
Okay.
It will. It always will be. And one thing we gotta do now, we gotta talk about doing triple integrals and spherical coordinates. Let's talk about the volume element. Now with polar coordinates and double integrals, the polar coordinates, the area element was RD theta. Right? It was RD theta. Now we have rho d phi, RD theta in this d rho. Do you notice that? Well then we gotta put something for this. We gotta put, so excuse me, these are fine, but which variable in here is not one of these 3? So we gotta substitute it, and then we'll make up the volume element. Kind of like that RD theta we had for polar. Which variable? Do you all see it? It's the R. So we're gonna have to put something in place of that. So let's use this. You'll notice it comes down to 2 right triangles here. You got this what? You got this one triangle that is, I'll draw it again right here. There's like an X, there's a Y, and there's a R, right? And there's theta. What's the other right triangle? I'll put it right next to it. What's the other important right triangle that we have?
R rho z.
You got it. So I'm going to put it right here. Now when it's in this image, but I just wanted to draw it again. You got rho, you got Z, and you got an R here. And where's phi? Be careful. Is phi here or here?
Phi is
Look carefully in that image.
between rho
That
and
right
z.
triangle, phi's up here. Does everyone see that? Be very careful. I think it's easy. This comes down to, it boils down to 2 right triangles in there. And there's a phi right there. Because it's equal to that angle, which is outside that right triangle. Cool? So, what were the equations back in polar coordinates? Well, I had x equal to r cosine theta, and what was y equal to?
Sine theta.
Or sine theta. Well, I'll leave that there. So we're going to need something new for spherical coordinates. It's not going to be hard. It's coming from this triangle here. Everyone, can you tell me the relationship between r and rho? So I can substitute something for that r. It looks like r and rho, you know, SOHCAHTOA. Opposite of phi, and you got this rho. What's sine of phi there? In that right triangle. Opposite over hypotenuse?
Yep.
So what is r equal to? And I'll leave it on the board, all class.
Rho sine phi.
That's what r equals to in spherical coordinates. If you're like, oh, I gotta memorize it. Sometimes it's not really memorization, it's just drawing a picture and just looking at it. But I'm gonna leave it up all class. R is always equal to rho sine of phi, as you can tell in this right triangle. So, this is all I need to make spherical coordinates. That was polar? That was polar, right? Then what's spherical? What is spherical? X equals, I can just replace this r with a what? A rho sine phi. It's going to look long, but there it is. That's what x equals in spherical coordinates. Does everyone notice? I just substituted the rho sine phi for the r. What will y equal? I know they look long. Welcome to spherical coordinates. But this actually makes problems easier. Can you believe that? We wouldn't, I know. People are shaking their heads like, what the heck? Makes some problems that deal with spheres and cones easier. What does y equal to? Rho sine phi sine of. Now we need one more variable. What's z? That's going to be easy. Just go back and look at that triangle.
Z goes to.
You'll notice it's something with a cosine, isn't it? Because z's on the adjacent side of phi. So what's the cosine of phi there?
Z over
Cosine
rho.
of phi is z
Over rho.
over rho. So guess what z is?
Cosine.
Just rho. It's short. It's not long like the x and the y. There you go. And those are the three conversions. But you'll notice something. It's like, oh, I got to memorize this. More than memorization, it's conceptual understanding. Seeing what these triangles are, and you can build it yourself. All I did was take polar. All I did was take polar and replace the r's with the rho sine phi. That's all. But I had to look at this triangle though again to see what would the relationship between the z and the rho be in terms of phi. So z is equal to rho cosine phi. Cool. There they are. Leave them up all class. I can move this over and just put them right here because they're long. X is rho sine phi cos theta. Y is rho sine phi sine theta. And lastly, z is rho cosine phi. Leave them up all class. Everyone go with that? Nice. We should add one more then. We should definitely add one more. Write them right there. Put that down so we can see it. Pythagorean theorem. R squared plus z squared equals.
Rho squared.
Everyone agree? What was r squared back in polar? X squared plus y squared. So guess what we got now? X squared plus y squared plus z squared is equal to rho squared. Does that look familiar? Isn't that the equation of a sphere on the first day of class in section 12.1? How cool is that? We're in section 15.9. That's the equation of a sphere. X squared, except we use the letter r, remember? We use the letter r. From now on, we'll use a phi. Or excuse me, we'll use the Greek letter rho. So it looks like a p. That's the equation of a sphere. X squared plus y squared plus z squared must equal rho squared. So back to this. So let's just write this out. What will triple integral? You know, a function of x, y, and z. You know, in Cartesian, what will this be equal to? Okay. Well, it'll be, I think I have enough room, because these are long, aren't they? F of rho sine phi cos theta, rho sine phi sine theta, rho cosine phi. And I'm about to put down d rho, d phi, d theta. But there's other stuff. And I need you to focus in on this, everyone. Right there, this three-dimensional object to figure out what's the volume element for spherical coordinates. It's right here. It's got a d rho, it's got a rho times d phi, that would be this side. See this three-dimensional box that I made there? I know, it's almost like just a speck, it'd be infinitely small. D rho meaning really, really small part of rho. This is just rho times an angle phi, but I'm thinking like infinitely small, like change in phi, d phi. But then this part. That was r d theta. What can I substitute for r again? And I'll put it right now. What can I put in place of the r? Rho sine phi. That's that little dimension there. So see it's like a little three-dimensional object there. It's got this side, and this side. Well, d rho d phi, but the r d theta is now rho sine phi d theta. So when we put boxes on three of these, we're going to put it as a volume element. It would be this, and all of that. And that's going to be my volume element, the product. Length times width times height. How many rows you got in there, though? You got two. It's a rho squared. Everyone see you got a rho times a rho making it what? Rho squared, and then there's a sine of phi, d rho, d phi, d theta. D rho, d phi, and d theta. I got all three. There it is. Put it up here too. Leave it up all class. It's equal to triple integral f of rho sine phi rho sine phi cos theta rho sine phi sine theta rho cosine of phi. It really gets long, doesn't it? This is over some p, these are the limits. And I'm going to have, what's automatic? I'll put it in yellow. This is like not forgetting the r in polar. Rho squared sine of phi. That's the volume element, the spherical coordinates. And you got d rho, d phi, d theta. Leave that up. All class. Okay. So let's look at a problem where spherical coordinates will be helpful. I want you to first do it in Cartesian so you see why this is going to be helpful. You know, the first. I mean, how is this going to be beneficial to problems? Look at all the writing on the board. I just want you to examine this. There's a lot of stuff going on. This is all for spherical coordinates, this section. So how can this be like easier for problems? Well, let's think about getting when I got a sphere. Let's try this in Cartesian. The sphere has a radius of 2. Okay? And I'll draw. Can you help me in Cartesian figure out the triple integral that allows us to get the volume of the sphere? I'm going to draw a sphere. The radius is 2. This is a full sphere, and I want you to help me figure out the volume. Make sure it looks like a ball. And the sphere is centered at the origin. So if I do Cartesian, what would volume? I'm doing this for a reason, so you see why spherical coordinates is helpful. Triple integral of what number gives me volume? Triple integral 1, dz, dy, dx. What's the equation of a sphere with radius 2? Oh, we were just talking about it. x squared plus y squared plus z squared equals 2 squared, which is what? 4. If I'm going to talk about the top surface, I got to solve for that top z. I need the equation of the top hemisphere for my top z. Look, I need this top surface right there. What's the equation of that? If I solve for z, you get a funny looking what? It gets long. It's a long square root. 4 minus x squared minus y squared. Okay, I'll put that in. 4 minus x squared minus y. Woo. What would be the lower limit? I want the full sphere. The lower limit's down here. What's the equation of that guy? That surface down there. The equation of that surface is just, if I solve for z, it'll be negative that, right? Put that here. That's that hemisphere underneath, representing that surface. So far, so good? What do we call this thing in here? This right here, in between these two intervals right here, we call the projection onto the xy plane. What is the projection of a sphere onto the xy plane? What's the widest region ever encountered in that sphere? It's a what? It's a circle. And anybody know what the radius will be? You got to figure out what's the radius of that circle right there. I have it in white, so I'll leave it in white in terms of white chalk. What's the radius of that circle? That's our projection on the xy plane. Well, in the xy plane, z would equal what?
0.
0. So if I make that a 0, can everyone tell what that disk would be?
2.
It'd be a radius of 2. So that's our projection onto the xy plane. That's going to go here. I'll do a radius of 2. But you're noticing you got a lot of radicals in this expression, don't you? So if you help me create that, describe that, what would be the top? You solve for, this would be the circle x squared plus y squared less than or equal to 4. Solve for y in the top, what would it be? 4 minus x squared, what would be the bottom limit? That'd be that bottom semicircle, negative 1. Don't see what's going on here? This will work the problem, but it's very, very what? A lot of radicals. It's more complicated. Oh, these have to be numbers. What are they? What's the limits for x? Negative 2 to 1. Negative 2 to 2.
Professor, shouldn't that be dz, dy, dx?
Oh yeah, thank you so much. Thank you very much. dz, dy, dx. This would go from negative 2 to 2, negative 4 minus x squared, to square root of 4 minus x squared, negative square root of 4 minus x squared minus y squared to the top one. Cool. This would represent the volume in that sphere in Cartesian coordinates. So to solve this, would it be easy? That's what we're saying. This would be very difficult. What if I put that into a calculator? Well, it depends on the calculator what year it was designed, right? I mean, I put that in a TI Voyage 200. It might just run in an infinite loop. I'm talking about typing this in. You can try it on websites. Just type that in and see if it gives you the volume. You all know the volume of the sphere. What's the volume of the sphere in geometry? 4/3 pi r cubed, right? I mean, you can see if it works out for you. They give you the math. This is going to be way easier in spherical coordinates, okay? So that's our challenge. I want us to do it right now. We're going to find the volume of a sphere using spherical coordinates with a radius of 2. It's going to be a lot easier than this. So can I raise that? That's why I wanted to start with that. See how crazy it gets? Challenge. Let's do this. But we're going to go spherical. Spherical coordinates. It'll be way easy. Get the volume of the sphere. We don't need to get those radicals. Now get the volume of this entire sphere right here. Alright? Whoop, whoop, whoop. You don't need too much room. Triple integral of what gives us volume? 1. Everyone got that? Triple integral of 1. But if I'm going spherical, what's automatic? With polar it was an R. What's now automatic? Rho squared sine v. There's that volume element. So I automatically have to write down rho squared sine v. Isn't that interesting? You say, well, volume is triple integral of 1, but this is automatic as the volume element when I go spherical coordinates. It's just automatic. This is equal to dz dy dx with the d rho d phi d theta. I'll put that way again. D rho, d phi, and d theta. Cool? But you'll notice this is going to be really, really cool. We're just going to get numbers now. No more of those radicals! So let's start with this. This is going to be rho's. What's the limit for rho? I hope you find it real easy. How far out from the origin did you go to every point on that surface? 0 to 2, 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 0 to 2. What's the limits? 0 to 2. Okay, cool. Let's go to theta. Go all the way down to theta. Here's theta. Remember, theta's like this. Theta's like this. What's theta to get this whole sphere going? 0 to 2 pi. You got it. Theta 1, 0 to 2 pi. I'm telling you, spherical coordinates, once you get it going, it may look intimidating, but it's pretty cool and it's pretty easy. What about phi? Phi we gotta be careful on. What's the limits for phi to form the full sphere? So it had to open up from the positive z-axis, which is phi equal to what there? 0. Phi equals 0 right here. Right? I can even put it right here. Phi equals 0 here. But you gotta open it up how far to get the full sphere? See, if you stop here, pi over 2, you only get the hemisphere. You're going to go all the way down to the what? The negative z-axis. And what's that distance for phi?
Pi.
There you go. You want the full 0 to pi. And there you go. And let's work out all the math, and we should check this in the end. What's the volume of the sphere in geometry class? 4/3 pi radius cubed. We'll check that. It should come out identical, right? So when you get home, if you got a brother or sister in geometry class, show them this. No. Say this kind of really shows you why the volume is equal to 4/3 pi r cubed. You can prove it to them through this method. Just draw this, draw this, and then just go over here and put a 1. And just label this as an R, right? Okay. Question, can I break this up? Because you know I like to split things up if I can, where I don't do it as an iterated integral. Well, the rule is these have to be what? All numbers. Are they all numbers?
Mm-hmm.
Cool, that's number 1. Number 2, I have to be able to write these as products, as separate variables. Can I do that? Yeah, so I'm going to do that. I'm going to split it up. So you got a 0. It makes it easier. 0 to 2 pi of the what? Just the d theta. Then you got a 0 to pi of a sine phi. And then you have the 0 to 2 of the what? That's how I do it. I don't do it iterated if I don't have to. Do that, do that, do that. Multiply, get the product. What's that? It's 2 pi. Done there. What's integral sine? Cos or negative cos?
Negative.
Okay, be careful. Negative cos. Let's plug in a 0 and a pi. This one, you got to be careful on this because there's a lot of negatives. The cosine of pi is negative 1. So look what I'm getting. Negative cosine of pi. Negative, negative 1. Subtraction sign, negative 1. Be careful. What is that number?
0.
This should be positive. We're getting a positive answer. This is going to be volume. What is all that?
2.
What, right? That's a 1. 1 plus a 1 is 2. Does everyone see that? Be careful. That's the number 2. So 2 from this one. 2 pi from that one. What's rho squared? Oh, that's just rho cubed over 3. Go from 0 to 2, what do you get?
8/3.
So the answer is 8/3 times 2 times 2 pi. That's the volume. Volume, the whole sphere. Take this, multiply this, multiply this. Volume equals 2 pi times 2 times 8/3 or, what's that?
32 pi over 3.
Now I'm going to check over in my geometry class. I was told volume of the sphere was 4/3 pi radius cubed. 4/3 times 2 cubed. 4/3 times 8 is 32 pi over 3. Isn't that cool? But we're going to look at some other things. What if you stick a cone inside of here? What if you got to find the volume between the cone surface and the sphere surface? Okay, that's what we're going to look at. I do want to point out. What if they stuck a cylinder inside of here and they went go back to cylindrical coordinates? I'm telling you. This is not good with cylinders. Do you notice that? Because the nature of, how does phi operate? Right? Phi operates like this. See? Coming out from that positive z-axis, that angle. That doesn't make it very helpful with cones. Cones just, I mean a cylinder. Cylinder's good. It's all raised it. So here's the next problem. I'm doing one. Let's do this. This is number 2 from the practice problems I just handed out. We won't do the multiple choice that was in there, but we're going to find the volume of the region inside the sphere, x squared plus y squared plus z squared equals 16. I'll erase all this. Now let's find the volume of the solid inside the sphere. X squared plus y squared plus z squared equals 16. And what else did they write? Region inside the sphere, what else? Above the xy plane. Okay. That just limited phi. See what they're saying, everyone? Above the xy plane. That just limited this phi here. And below, below the surface of the cone, z equal to the square root of x squared plus y squared. And when we're talking about a cone like this, so we got to talk about that right now. And what angle will always be formed, cone out like this for a cone with that equation? We should just talk about that. And just take the cone right now. We've seen that cone before. This is coming from section 12.6. 45 degrees, right?
Mm-hmm.
So what would phi be always?
45 degrees.
I need you to know that. There you go. Phi is going to be pi over 4. So that when you recognize that cone equation, you're like, is phi is always going to be pi over 4? That, yep, that's the angles coming out of it. Forever and ever, right? It's an open surface, so it just keeps coming up. It opens up in a circular manner. It's a circular cone. Pi over 4 is what phi is coming down from the positive z-axis. I just want to make a note of that. We got to find the volume of the solid inside the sphere, above the xy plane, and below the surface of this cone. So I'm going to draw this again. Let's make an image of this. And here's my sphere. Right? There's my sphere. And where's the cone? The cone's going out like this. There's the z-axis, the positive z-axis. Phi is right in there. There's phi. We need what volume? The volume is got to be inside the sphere, above the xy plane, but below the surface of the cone. So when we're shading, look right here. Would you shade around there? Then we'd shade like this all the way around. Just think that's what we're shading. So maybe make like a little kind of circle around like this. So you can see that's how it would form all the way around. That's the region. It's inside the sphere. It's above the xy plane, but it's below the surface of the cone, because that's what they're asking for. Okay. Well, then we're going to go spherical on this thing. You ready? So everyone, where are we? It's in here. We're thinking all that in there. Below the surface of the cone. Like that, all the way around. Like that. Inside the sphere. So, let's go spherical. What's automatic? Rho squared sine phi. A d rho d phi d theta. A d rho d phi d theta. Let's start with easy theta. What's theta? 0.25? That's easy. What's rho? It all depends on this. No tricks. What's that rho going to be? How far out do we got to go for this here? Remember, that's rho squared. Rho squared equals 16, just the distance out what? 4. That's what's going on in that shaded region. In that entire shaded region, you're always going from 0 to 4. There's your limits. That's easy. Well, here's the challenge. What is this? I say we'll label this, make sure we don't mess this up. You know, is that 0 to pi over 2? Is that 0 to pi over 4? Is that pi over 4 to pi over 2? Is that pi over 2 to pi? You know what I mean? So let's label this. What's phi equal to right here? Phi equals 0 up there. What's phi equal to right there?
Pi over 4.
Pi over 4. So that's definitely got to be one of our limits. What's phi equal to right there in the xy plane?
Pi over 2.
There you go. We just figured out the limits. Excellent. We're going to go from, look, pi over 4 to pi over 2, all the way around. What brings it all the way around? The theta. The theta will just swing it. Isn't that cool? The theta swings it all the way around. We're going from pi over 4 to pi over 2. We put the lower limit there. Cool. You don't have to work this out. It was just a setup problem. You know, find the volume, that'd be the setup. But I know you can do this integral. Look, break it up. We did before. The key is, can you set that thing up? I know you can solve all these. We'll solve one of them though. We'll eventually do another one. Evan, great job with that. And when I want to switch this up and do a problem like that last one on here, the wording has changed slightly. Okay? Find the volume. Use spherical coordinates to find the volume of the solid that lies, this time, within sphere. That was the wording. Isn't within the same thing as inside? Good. Within the sphere, I'm going to use the same 16. Does that sound good? No, let's do that one right there. Let's use a 4. Use the same one on that sheet. Above the x-axis, but this time, above the surface of the cone. Same equation. So that gets a whole new setup. But it's not much different, is it? There's my sphere. There's my cone. And where am I shading? Within the sphere, here's the sphere, above the xy plane and above the surface of the cone. Okay. Above the surface of that cone. Where am I shading?
Above.
What does this look like?
Pizza pie.
It's like an ice cream cone. Yeah, right. Because it's three-dimensional. I'm thinking, right? It's like an ice cream cone. That's what it looks like. It's got this thing and it's all the way around, right? It's got that little ice cream on top. Because it's within the sphere, but above, there's the surface of the cone right there. It looks like a V when I'm drawing it on the board, but it goes all the way around. All right, so what do I get now? What's theta? Still the same, 0 to 2 pi. We'll come back to phi. What will rho be? What's that radius?
2.
Oh, 0 to 2, 0 to 2, 0 to 2, 0 to 2, 0 to 2. This is going from 0 to 2. And they said volume, so I'm just doing rho squared sine phi. That's my volume element. D rho d phi d theta. Cool? What's phi? Pi over 4 to pi over 2. 0 to pi, pi over 2 to pi, 0 to pi over 4. Let's go through this again. What's phi equal to right here?
0.
Right. Phi equals 0, positive yes, and then it opened up. And it stops right here. What did phi equal there?
Pi over 4.
You got it. You understand spherical coordinates. Outstanding. I can tell. You got it. 0 to pi over 4. That would give us the volume that I can go. Cool? This is way easier than, imagine doing that in Cartesian. That's what we're saying. That would be a pain. Right? You can still do it, but it'd still be a lot of work. You'd have radicals. You'd have radicals going on. You'd have that radical, but you'd have more radicals with that top surface. We can work this thing out. Let's work that out. This time we'll solve it. This time we'll solve it. Settle it. All right. Can I break it up?
Mm-hmm.
Let's do it. 0 to 2 pi, piece K, P there. You got a 0 to pi over 4 sine of phi. Okay, that shouldn't be too bad. And then a 0 to 2 over rho squared. That should be easy too. That's rho cubed over 3. Oh, that's 8/3. This looks like the problem we did earlier. 0 to 2 pi, that's 2 pi. Looks like the problem we did earlier. What's this though?
Negative cosine.
Okay, the only thing is, you're going from 0 to pi over 4 this time. Anybody know the cosine of pi over 4? It's got a radical 2 in it.
Root 2 over 2.
Root 2 over 2, or 1 over root 2, whichever way you want to say it. I'll do root 2 over 2 because you said that. So I'm going to do negative root 2 over 2
Plus 1.
minus negative cosine of 0 is.
1.
So what's another way to write that?
Plus 1.
So negative root 2 over 2 plus 1. I can't simplify that. So I did like common denominators. I've got this times that. That's my volume. I'll leave my answer like that. So volume equals 2 pi times 8/3 times 1 minus root 2 over 2. Unless you want to make the 2 times the 8 what?
16.
16/3 pi. And if you want to distribute it, you can knock out that 2, but this is fine. You know? 2 pi times 8/3, 16/3 pi times 1 minus square root 2. That's your volume of the ice cream zone. Cool? And you got it. I get worried about not number 3, number 4. So I'm going to write it on the board. You see number 4? On the practice problems that I handed out today. I try to really make it really big, bold-faced print. They go, hey, what's the integral of this? They didn't say anything about volume. They said evaluate this integral. X squared plus y squared plus z squared. Okay. Where E is the solid, here's E. E is the solid. X squared plus y squared plus z squared. If it's a solid, they got to use an inequality less than or equal to 1. And I didn't want your eyes to miss this. Comma. Don't see that? What does that mean? If our eyes miss this, we're going to set up the problem incorrectly. That means this solid has to be above the what?
XY
plane. Okay? Has everyone got that? So if our eyes missed that, I just didn't want that to happen. So do you all have your problem sets handy? Did I have, look near the end. I don't remember. Well, not 22, not 23, 24. I would like everyone, if you have it with you right now on 24, highlight it or circle it. Do you see that z greater than or equal to 0? It's small. It's like, if your eyes miss that, you're going to be choosing, the wrong answer. I'll wait till you get there. 24 in the problem set. Yeah? Everyone see it? Just highlight it. Hey, don't worry about it. There's a little beep, and you, oh, that means I'm not going all the way down. It's like I'm stopping above the xy plane. That's what that means, above xy plane. Cool. All right, so everyone, we just got to set this thing up. Then evaluate this integral. All right, let's E is a solid. X squared plus y squared plus z squared less than or equal to 1. Hey, does this have anything to do with that? No, it just so happened that they had that in. So we're going to go with spherical coordinates. So I'm going to start out. What's automatic? Rho squared sine phi, right? This is the first problem today. I've got something else in here. I can't leave it like that. I'm not allowed to need x, y's, and z's. I need rhos and betas and p's. Anybody know what that's equal to? That's rho squared. So I'm just going to draw an arrow and go, you're rho squared. Isn't that cool? That's rho squared. Is the automatic volume element. A d rho, d phi, a d theta. And we're talking about a full sphere, but the sphere is above the xy plane. Everyone got that? Full sphere, above xy plane, oh, hemisphere. A top hemisphere with a radius of 1. So let's start with rho. You know what that is? 0 to 1. Here we got that. What's this then? What's phi? That's the tough one. Above xy plane. 0 to pi, is that pi over 4, pi over 2, or pi?
Pi.
You're good, that's 90 degrees. We're going from 0 to pi over 2 to get down to the xy plane, right? To give you that hemisphere. Or do 0 to pi. That's the answer. What's this? Nothing different here. If they said like first octant or something, we do 0 to pi over 2, but this is going, theta is going all the way around. So theta is going to stay what? Always think theta like that. There's a setup. You can split this up thing also, right? Rho to the 4th. What's the integral of rho to the 4th? Rho to the 5th over 5. What's the integral of sine phi, negative cosine phi? Plug in pi over 2 and 0. 0 to 2 pi. Hey, great job with that. Let's do number 5. Can I raise? Cool. Yeah, alright, it's number 5. Let me write all this out. So we're going to find the mass of a solid. Okay, this time it's not volume. You agree, when we find mass of a solid, it's a triple integral and we need the density. So they're going to give you the density. The only thing is you'll notice they'll give the density in a different Greek letter. They used to give it in rho. So we'll just put it in, you know, something. You'll notice the notation is something different. Mass of a solid solid region between spheres x squared plus y squared plus z squared equal to 4. And what's the other one? X squared plus y squared plus z squared equals 25. Ooh. This would be really challenging in Cartesian coordinates. This should be a piece of cake in spherical coordinates. And what's the density? Where the density is, okay, they use the Greek letter sigma there. Sigma equals, this is the density, xz. Are you ready? What's the automatic volume element?
Rho squared sine theta.
Rho squared sine phi. Rho squared sine phi. A d rho. A d phi d theta. Well, I'm going to put that way down here. My d rho d phi d theta. You know why? Where's this going? That goes in here, right? But this is wrong, isn't it? I leave it like that. That's an x, that's a z. My variables are rho, phi, and theta. What was x equal to? Better leave yourself enough room here. Remember these are long? What's x?
Rho sine theta.
It's long, look at it, right there.
Sine phi
Rho
cos
sine phi. Alright, here we go. This is that x. I'll draw an arrow. Rho sine phi cos theta. And what's z?
Rho sine.
Z is rho.
Sine phi sine theta.
Remember, z is just rho cosine phi, though, right?
Oh, so it's
Rho cosine phi?
Z, yes.
Yeah.
I think of y.
Right. But if they had a y, I would have put that. I would have put there was a y in there. Like, if it said x, y, z, it didn't say that, did it? No, if it said x, y, z, this thing would have been even longer. I would have had to include that long y. Now, what's the limits? I hope you find this easy. If it's between those two spheres, what's the radius of those two spheres so I can get the rows? Radius is
2.
2, and what's this radius? There you go. Between a sphere of 2 and a sphere of 5. Yeah. The region inside. Did they say anything about above xy plane? No. So phi gets to go what? Let it open up to get the full spheres. From 0 to
Hi.
pi theta. They didn't say anything about the quadrants, right? They didn't say about like only an octant 1. If they said octant 1, then we're doing 0 to pi over 2. This is just full 1. And we can definitely make this look a little prettier, right?
What if they said like octant 2 to 3?
Oh, I like that. Octant 2 to 3. Octant 2 to octant 3. That would be, this octant 1's here, we'd go from pi over 2 to the pi. That would mean over there. That means on that next door over on that side. And they never do that if you're curious.
Alright.
They either do octant 1 or they say above xy plane or they say below xy plane.
Alright.
I know, it's a good question. They'll never do like octant 7 or something, right? Man, excellent. Excellent. Any questions on that? Okay, cool. And I'm going to put this back, 0 to 2 pi. Hey, the book, I wanted to show you this. The book had a question. It's going to look something we did similar here. They had an image, and they wanted you to set up a triple integral to figure out what it would be. So I'm going to put that up here. I'll let you copy that. I just want everyone to see this. I'll fire that up. Does it make a noise? Oh, good, the light's going on. All right. Last thing. The reason I wanted to pick this up is your question. This is the last thing we'll do. Any questions? You got spherical coordinates now. First, I wanted to point out, and this is just a page from the textbook. You know it's got the same stuff we're talking about, so please feel free to read that textbook and see the same stuff we had on the board here. But the problem I wanted to go to had an image. We got to set up the volume of it. And that was it. And I'll hit the light. And when you see number 20, I'll just zoom in a little bit. There we go. Number 20, hit the lights. Because this is based off, I know you said about octant 2. Well, did they ever give you an image of something else? So look at number 20. Can you set up a triple integral of an arbitrary continuous function of x, y, and z in cylindrical or spherical for that right there? We won't do that. Do you agree this problem we do cylindrical coordinates? That would be easy in cylindrical coordinates. But how about that? That's going to be a lot easier in spherical coordinates. You see how it's a portion of a sphere that's got a hole in the middle. So we're going to set that up. And we're going to set it up over that solid. Sound good? Oh, question?
I was going to say, wouldn't it just be the same thing except theta would be pi over 2 to pi?
He's only moving theta. He says you just got to move theta. And what does phi do? D goes from 0 to what?
Pi over 2.
Pi over 2. That's it. I'm going to put it right here on the board. They said an arbitrary function of it, so I'll just write this. See this part? I'll just write that. Say it's just some function of what? An arbitrary function. And you got it. Now put the lights on. Ready? This is for that image right there. But he says you're going to go from, what was that? Pi over 2 all the way rotate around to 2 pi. That's what theta is going to be. This is theta. He said d was 0 to pi over 2 because that stopped in the xy plane. And what was that radius? Oh, can you hit the light? Can you see it? Radius between this, there's a hole in there. It goes from a 1 to a what? 1 to 2. There's those limits. This is automatic. But then he said just set up for an arbitrary function, so I'll just write this. Function of that. I'll just add it. Here, function of rho sine phi cos theta. Got enough room? Rho sine phi sine theta. Rho cosine phi d rho d phi d theta. Cool. Excellent. I just wanted to make sure. Is there any problem where they do that? Well, they would give you an image, so you can really kind of see what's happening there. Like that. Cool. Hey, that's it.
No.